that pertain to LSST in one way or another. The first of them is to be given by Tony Tyson, who's a distinguished professor of physics at the University of California at Davis. And I just want to take one moment to say that he's a personal scientific hero of mine. Tony pioneered moving from being a physicist into a fundamental physicist using astrophysical tools and techniques. And I look forward to his presentation on weak lensing using LSST. Professor Tyson.
It's great to be here to celebrate Steve's career to date, I think.
Oh, well, it's on officially. 1, 2, 3, 4. Can you hear me? I'm not in control of volume. Good. Okay, cool. So one of the original motivations for LSST, in fact, was this. Mainly, in fact, its name wasn't LSST as a result of it. Mainly to map dark matter throughout the large volume of the universe, to look at the evolution of large-scale structure. So what I'm going to do now is sort of bring you up to speed on what I think is the current state. And I'm not going to talk just about LSST because this is now going to involve space observatories as well. But just first of all, I think that we can do with LSST, what's being done now, and then what we might do with LSST and space observatories together. So this is, you've seen this drawing we made back at Bell Labs a long time ago, probably before, but it tells you geometrically what's going on. You have a distant galaxy, which let us say for right now is intrinsically round, and each one of its pixels gets mapped to a new place in the sky by the light bending due to the intervening overdensity of dark matter, and you're down here looking out, and you see instead of this, you see everything moved over here into this sort of banana-shaped thing, and this is a sheared thing that has a shear, which is a combination of geometric cosmological factors having to do with distance ratios, angular diameter distance ratios, and gravity. If you go in and want to fool with gravity, you can change this other term. So it's a mix of these two things, and you have to do some other experiment to break the degeneracy. So this is almost state-of-the-art from the ground. This is fairly recent data from Subaru, where we've got a field of number of arc minutes across, and you can, if you look at the colors of these distant galaxies, you can see sort of a concentration of faint reddish things here. The contours in white are the dark matter densities obtained from weak gravitational lensing of about 40 galaxies per square arc minute, which is the ultimate goal for LSST weak lensing. And we did this in Subaru without selecting data. It was just we went there and got some data and came back, and it's galaxies 25th magnitude. The seeing was 0.7 arc seconds. It can get better than that, but that's what we had on that night. This is a cluster of 10 to the 14 solar masses at a redshift of about half. There are challenges in this business, and it's not like falling off a log to make a map of this like this. You have to correct for a lot of things. And the real challenge occurs when you're not looking at massive things like this, but just the general cosmic large-scale structure mass, which gives rise to a much smaller shear signal and has in it, encoded in it, far more information. We'll get to that. In fact, right now. So this is what happens when you consider the more general case where you have cosmic shear. You have some distant galaxy images like in the previous cartoon. Two galaxies that might actually be different in shape, of course, because they're different. But they're close together in the distant universe, and their light from them suffers the same angular distortions due to the intervening overdensities of dark matter. And you see a correlation induced between their shapes as a function of distance. You go bigger distance, and you see a decorrelation because the light from galaxies elsewhere in the sky goes past different overdensities. And so the shear correlation function has embedded in it useful information, not only with regard to the total net distortion in the universe, in other words, related to the total mass density, but also tomographic information, because you can do this over and over again for distant redshift shells. You can select color redshift shells for your distant galaxies and do it tomographically. So to do all this, here's the difficulty. So you want to measure this shear. It's actually rather small. The shear around a cluster of galaxies might be, a few percent. However, the shear in the middle of nowhere, due to this cosmic shear, is 10 to the minus 4, typically. That is actually challenging. And what you want to get from the LSST specifications for this, to do our cosmology for dark energy, you can express the shear as a combination of terms. The actual measured shear is the true shear times some kind of prefactor, where you misestimate the true shear because the galaxies become more rounded, for example, by the atmosphere, by other systematics. Anyway, there's this multiplicative term, and you've got to get this extra factor m in it, smaller than about 3 by 10 to the minus 3. And then there's this offset, which is actually a little easier to handle. A systematic error, everything in the image, say, or in that vicinity is sheared by a certain amount. That you have to get a factor of 10 better on that. The thing that saves you is the fact that nature has been so kind as to place calibrators all over the sky due to foreground stars in our own galaxy, which generate point spread functions at various places in the image, which can be then used to calibrate this. But then, of course, you want to go beyond that, and you want to calculate the shear correlation function. And you can see that the surviving two terms, you are very sensitive to this multiplicative offset, and of course to this additive term. There are various diagnostics, which I don't have time to get into, but that we've developed over the decades to try to analyze metrics, to try to analyze the magnitude of these systematics, and in fact to correct for them. And we're making sufficient progress that I'm really optimistic that we'll be able to get to these levels. So this is a nice cartoon made by Sarah Bridle, where she shows where you start out with an intrinsic galaxy. It gets lensed, distorted, stretched. Then the atmosphere fuzzies it up. Then you have the pixelization from the CCD, and then you add noise. And this is the signal that you deal with. And then the calibrator signal, these nice stars that nature has placed throughout the CCD. You have a star, which is just a delta function, which cannot be seen on this projector. The atmosphere fuzzies it up. You get pixelization, and then you add noise, and you get this. And then you have to you don't want to do the obvious thing, which is a full inverse solution to this inverse problem, but you want to do a forward calculation, which allows you to account for this effect in the PSF, and I'll show you how that's done. So this is a simulation we did a number of years ago for LSST. You can see the footprint of the LSST CCD array there, 189 sensors, 4K by 4K. This is only with the atmospheric shear distortions turned on, and all you see these sticks are all the stars that are in the field. You don't see the galaxies. So this is the stars that will be in that typical LSST field, which is about 10 square degrees. And it's an atmospheric effect. The atmosphere is moving the stars around in the sky. And it's shearing their shapes, and so their PSFs vary in a sort of a continuous way, but I'll tell you in a minute, it ain't so. But in this simulation, we assume that the shear is a continuous thing as a function of position, and developed, with James G., developed a principal component analysis of the shear of the stars, and we apply that analysis to the data, and you can see on the right that we corrected, it turns out adequately, for the atmospheric effects, due to I think we used 7 layers of moving atmosphere layers adequately to do the cosmology. This doesn't solve all of the problem, because you've got to get, even if you believe this, you've got to get to the position where your galaxy is, which is at a different place. So there's this extrapolation difficulty. Well, we have done some tests, more recent tests, to show that that might actually work for LSST if we do certain things. So just to give you a level of, I don't know if this laser is bright enough. Is there another laser? This laser is dying. Anyway, that blue line that's up there is the atmosphere plus optics which I showed you before. It's pretty hopeless because the signal you want to detect is that sort of yellowish cosmic shear line there. This is the shear correlation function, gamma gamma. So you want to get, remember, you want to get down to where that green stuff is in terms of your error. Thank you, sir. Great. Yeah, so this is the signal, and this is where you want to get, and this is where you are. So then you use, then you say, okay, well, let's just look at the atmosphere only. Let's turn off the optics. And so you're only down to here, which is still pretty hopeless. But once you apply all these PCA algorithms and turn the crank and use all the stars in an optimal way and correct for both of the additive term and the multiplicative term, the red stuff is what we see in our current simulations. This is a bunch of 15-second exposures with LSST, and it's the residual point spread function shear correlation that's left over. And you can see, in principle, you can get a factor of 10 to 1 out at many degrees, which is the scale of the cosmological signal from large-scale structure. So the question remaining is whether we can actually do that with real data. Well, we did that in the case of this Subaru data, but I think there's still work to be done. So how do we know if we're on the right track? Too many buttons, sorry. I'll get to that in a minute. So this is the current state of the dark energy survey PSF modeling, and this is within one chip. You have to do this chip by chip, by the way, because every chip is slightly different. This is okay. This is getting down. This is just the shear. So this is getting down to interesting levels of residual systematics, which are, competitive and certainly adequate for the science that DES wants to do over much of the chip, but not over all of the chip. And you can see things, peculiarities at the edges here, which I will talk about in a minute. These are thick CCDs. So how do we tell if anything is working? Well, you really want to do it in a blind fashion. So there's been a series of so-called shear challenges, shear estimation challenges, and the latest one was called Grade 3. And what they did in Grade 3 was to put out data which was sort of a realistic simulation of what will be found in the atmosphere due to atmospheric effects, et cetera. And our group joined the challenge, and of course the real answer was in a secret sealed envelope somewhere. The algorithm that we eventually have designed is called SFIT. So James G. Submitted his analysis of this data and got first place in all the categories, I think, in this Grade 3 challenge. This is the observed signal, and this is the signal after correction, and it's down at the level where I think we're safe. This did not include the effects I'm about to talk about, which have been discovered recently in our detectors, which is the subject of the remainder of this short talk. But before I do that, I just want to show you what we have been doing with the Deep Lens Survey, which is the sort of an LSST observing survey analog, but only over 20 square degrees instead of 20,000. And frankly, the seeing wasn't very good, and the telescope optics were horrible, really horrible. Mirror was floating around and hitting the edge of the mirror cell and bending and getting pinched and causing all sorts of bad PSF. But anyway, adversity can be a good thing, and we managed to correct for that. And what my student Ami Choi found is the first direct evidence using gravitational lensing for the growth of mass structures on large scales. Not just galaxy halos, but this is out at 10 megaparsecs. And you can see from a redshift of about 0.2 to a redshift of 1, the growth in cosmic structure over densities as you go from high redshift to low redshift. It had been seen before through correlations of galaxies, but never directly through gravitational lensing. LSST will have 50 times smaller errors than this, and so we'll be able to map the details of this. I alluded to the subtle features, which I'm going to mention to you now, of the current CCDs. We've always had issues with our detectors in any field of science, and CCDs have been giving us interesting challenges all along, but one of the biggest ones is right now that the current crop of CCDs is manifestly no longer two-dimensional. It's a full three-dimensional charge transport issue because they're so thick. And in fact, this is a Chris Stubbs figure, I believe, where the beam is coming in. It's an f1.2 beam, which is itself a bit of a challenge. And it comes into the silicon. The silicon in our CCDs is 100 microns thick, and the pixels are only 10 microns. So instead of the old picture we had of a CCD, we now have a picture of a pixel being a skyscraper. And there are all sorts of interesting opportunities for the charge carriers, the electrons, once photoconversion has occurred, to wander about, either due to space charge or due to lateral electric fields. Even though you put 50 volts across this puppy, they still can wander around. And so this is an issue. There are three general classes of such fields. One is that if you get a pile of charge from one of those bright calibration stars on a pixel, the next electron coming in says, whoops, I see a whole lot of folks there, I think I'll move over here. And so it causes a distortion of the point spread function due to space charge. There are impurities in the boule, in the silicon boule when they're grown. These tend to have a high frequency, spatial frequency pattern, and those manifest themselves throughout the fully depleted 100 microns. And then as you get to the edge of the CCD, there are electrode effects in causing fringing electric fields that cause pixel distortions. All of these effects are present. And in particular, as you get down from the original, where the photon comes in up here, you get down to the electrode structure, the polysilicon electrodes, there are channel stops here, and the channel stops themselves have implants causing electric dipole moments, and there are effects that we're just now investigating on the subpixel scale. So this is the brighter, fatter effect. I think this may be one of the first times it was found in one of the very early CCDs, thick CCDs that we had, and it's simply that if you measure the width of the point spread function in the laboratory, with an optical illumination, it's a function of the intensity. It just gets wider, as you would expect, and it's pretty much a linear relationship. But if you actually analyze, as Craig Leish has recently done, the electric fields in these devices, it's pretty complicated. And I won't go into this in detail, but basically the bottom line is you would really like to know what the geometry of the electrode structure is, and actually would really like to know what the doping is in order to do the calculation right. But we're making progress by modeling this. We actually do have to make measurements in the laboratory, but I'm just trying to sell the idea to you that at the moment, folks have been doing what we did in the old days, which is okay, but probably the wrong thing. Mainly wait until you're on the sky and say, oops, there's a problem. Maybe we should just use the data we have to try to understand the detector. And it's working for DES actually pretty well. But why not actually do this in advance in the laboratory? So we should just do everything we can to learn about these guys before we put them on the telescope. So this is the attempt, one of the attempts to do this. This is a machine which is about 10 feet long, scattering sphere, then it goes in, the light goes into a mask, a filter first of all, and then in a mask which has an astronomical scene on it. Right now we're just using a nice regular grid of 40,000 holes, stars, and it gets eventually through a bunch of optics projected onto the CCD, which is inside this doer, which is sitting back here, in an f1.2 beam, which fully imitates the optics of the LSST. And then we just scan this laterally, move this focal plane back and forth to imitate shift and stare imaging, and we get a whole lot of data. And this is an example from one of the vendor CCDs recently. This is a 16-channel device. Our CCDs are split up into 16 pieces because we have to read them all out in parallel in order to read the entire 3.2 gigapixels in 2 seconds. And so this is just a zoom in. The reason why it looks like it has measles is because it does. This is the result of projecting these 40,000 holes onto it. So now in the zoomed image, you can start seeing some of the holes. And what we do is we just move those holes relative, move the doer relative to the beam, and those holes move around. And we just take thousands of images, and so we get fractional pixel accuracy in these effects, looking at the pixel size changes, and the pixels, of course, are in the wrong place because they move around due to these lateral electric fields. So this is just jumping to the end of this, an example of what we find from a presentation that my student Andrew Bradshaw made at a recent meeting at Brookhaven, where what we did is we used all this multi-dithered 40,000 hole data to examine what happens as you move up towards the edge of the CCD. And this is one of the edges which is near the serial register. Okay. There are two effects happening here. One is horribly boring, and the other is very interesting and exciting and scary. The boring one is the fact that you're illuminating this thing with an artificial star, and the light from the star simply falls off the side of the CCD, and so there's an occultation going on. You can model that by taking all of the PSFs from the data and doing a forward massive Monte Carlo simulation, which is what he did. You can model that to high precision, and that's this solid line. That's the boring effect. The exciting effect is the pixel actually apparently gets sucked towards the serial register as you begin to approach it. It's not at the right place. A star is not at the right place. It's closer to the serial register than it ought to be. It's reported as being closer. And it gets sucked into this. Interesting. And it appears to be independent of intensity. That's good news. We don't have to correct for that effect, at least. So Craig Lage is trying to understand all of this by solving Poisson's equation, given all of the vendor information, at least from one vendor. So that's one effect. Here's a more interesting one, which is intensity dependent, just like the brighter factor effect is. This is as we approach the, right in the middle of the CCD, we put a channel stop, we put a bloom stop, which is just going to stop the blooming charge from extremely bright stars from going on to the other 8 segments above it. You save a factor of 2 in real estate. In the end, it turned out to be a bad decision, I think, to put that in, but because you see this funny effect. As you approach the bloom stop from either side, sure, you see the occultation effect, which is this gray line, but you also see charge level dependent distortions in the pixels. They're reported as being in the wrong place, and in fact, their shape changes. And you see this funny kind of behavior. This is all reproducible, and it's the same plot approaching it from either side. So we're going to have to understand these effects, because the intensity of these effects, I forgot to mention that, is rather large compared to the shears that I was talking about before. This is like 0.2 pixels. Multiply that times 0.2 arc seconds, and you discover that you have a very large systematic that has to be corrected to better than 1%. So the point is that with enough laboratory information and enough vendor information like this, like known geometries, known dopings, and known voltages, because we know what voltage we put on all the electrodes, we can solve Poisson's equation. We can find our copy of Jackson and make a model for that CCD and do what? Well, there's a lot of stuff we have to do. But the key thing, that I think the take-home message for the LSST data management group is that if we can come up with a model of the detector as a function of position on the detector, as a function of voltage, and frankly as a function of clocks, how you clock it, we can correct to first order for those effects in the data pipeline. We can treat each pixel, to first order, we can treat each pixel as having 4 corners, and each of those 4 corners is updated and adjusted according to the model. And so the output of the pipeline should be the corrected to first order astrometry. And also, I didn't have a chance to discuss the photometry, but that's also closely related. The photometric errors are closely related to the astrometric errors. Once we do that, we can go back and then see if it works. We can do null tests to confirm that it actually does remove the PSF systematics. We can actually play LSST in the laboratory and observe with stars and galaxies and create shears. Can we measure the science signals, and then we can know how well we're going to be able to do before we get on the telescope. So just to close, we did a simulation recently assuming that we have the full, the assumption that I used in the simulation is that we're going to be doing no better than the dark energy survey is currently doing in terms of reducing these systematics. Bear in mind that they did not have laboratory data like this to correct their signal with. They just use the observed systematics, which are apparent systematics on the sky from the stars. I'm assuming in the simulation that we do no better than that. Actually, I think we might be able to do a factor of 10 better than that. But this is the simulation assuming a DES level correction. And what you're seeing here is this mess here is, what we did is we ran out of computer time. So we did 100 dithered visits, including all of these CCD effects turned on, mostly edges and bloom stop. And that gives rise to this pattern. You can see it maybe out at the edge where we had only a few visits around. We didn't have time to cover the entire sky, so we just did one field of, one field of the camera and dithered in X and Y and rotation. If I were to show you the results we got for just dithering in X and Y, it would look horrible. So you actually do have to rotate the camera because shear is a 2-component object, and so by rotating the camera, you get to mix the 2 components and cancel some of these effects to first order. But you still get a rat's nest left over, and the question is, how big is it? Well, what I'm showing you here in color is the analyzed shear residual that you see here due to the CCD effects, presented as a inferred mass over density map. And so there's a level here that is obviously disturbing, but it's at a level that, and I'm going to show you in the next and last slide, I think that we can probably handle. And so suppose we can correct to that same level. And I mentioned that maybe we can do 10, I think we can do 10 times better. Suppose we just correct for that same level. How small of a shear can we go to? So here's a great science case, not cosmology. Perhaps we can actually take a look at a bunch of dwarf galaxies. So this is a simulation we just did where we took a bunch of 10 to the 11 solar mass dwarf galaxies at a redshift of 0.5 and said, okay, let's do gravitational lens mapping of the shear, the tangential shear around those guys. And this is the residual shear that we got from this analysis, and this is the expected signal due to these guys, including the halo-halo term and the cosmic shear effect. So it's a reasonably safe signal-to-noise ratio unless you get out to really large angles. But if you can do a factor of 10 better, that's even better, and I think we can. And if we do that, we'll have a sample of 10 to the 8, 100 million of these dwarf galaxies to probe the statistics of dwarf galaxy evolution as a function of redshift. That's sort of cool. We can also do cosmology. This is from the old science book. Now I think we really can reach these levels, and because at the time that we wrote this, we didn't know about these effects, but I think if we correct to them by first order, we can do this. We can look at the fractional distances as a function of redshift in the universe to better than percent. We can look at the growth of cosmic structure to on the order of 1% or 2. That's cool. We can just throw, you have a weird cosmological model, you can just throw it at this data rather than to try to use the, the W0, WA formalism. So just to conclude, there are a whole lot of ways in which the LSST can probe the physics of dark energy, of late time acceleration, and I just touched on a half of one of them, mainly weak lens shear cross-correlation tomography. There's something else that I didn't talk about, which has been developed recently, which is weak lens magnification tomography, which is complementary to that. And then there are all these other probes that LSST, the same LSST data, will make of the physics of dark energy. But, as they say, that's not all. It turns out that there are other missions. And so in particular, there's ideas of putting a satellite up to look at infrared, the infrared sky. So suppose you take the photometric redshifts from LSST, you have to know those to some degree. Just with our 6-band system, this is the photometric redshift versus the actual spectroscopic redshift. And you can see this, you can see the one line. You can see the line that you expect, but there's also catastrophic outliers which present some error, particularly in the covariance. But if you were to add space-based near-infrared data, it cleans up very nicely. So this is a nice collaboration with, say, WFIRST and even Euclid. We hope to do about 3 billion galaxies that are brighter than 25.3 magnitude. This is a so-called gold sample, and that's what this is plotting. So if you, recently there's a paper that's about to be submitted on the synergy between LSST and WFIRST and Euclid. Just as an indicator of that, calculation was done based on just assuming surveys by themselves, although the Euclid and WFIRST bars assume LSST 6-band photometry. But this is, so a bigger bar is better because it's the variance of 1 over the quantity. So this is the normalization, sigma 8 is the normalization of the mass density fluctuations. And you can see if you combine Euclid, WFIRST, and LSST, or frankly just LSST plus any one of those two, you get a better number by a bit. But then if you are interested in the neutrino mass, you can do even better because it's more complementary. So that's sort of fun. And I'm pretty confident that we'll be able to, with negotiations, share the pixel data because it's necessary. So that's it. Thank you.
We do have time for some questions.
Alex.
So what capability do you have? So you showed you can simulate a grid of stars, but can you also simulate galaxies? Can you go to low signal to noise? Can you?
I would have said no about a year ago, because the way we were doing it a year ago was to take little thin sheets of steel and shine lasers on it and burn holes. And it's hard to do a galaxy that way. But now we have used the same technology that is used in making our CPUs and our CCDs, mainly UV photolithography. So these are made photolithographically, and they can make anything you'd like. They can make a galaxy, a star.
That's great.
Yeah, so we're making those too. Sorry, you're in charge. You're in charge, guy.
Hi, that was really fun. Thank you. Do I gather that you think the detector is the limiting source of systematic errors for LSST weak lensing at this point?
I'm going to qualify that, yes and no. I think that if we can fully understand the atmospheric effects, which frankly are dominant, then yes. And so we have another program of research to use the information from the wavefront sensors around the edges of the imager to inform in a Bayesian sense, inform the inversion of, inform this PCA process in forming the PSF. And in fact, to be able to extrapolate the PSF from where that star is to where your galaxy is. And if we can do that, and the jury's out, but that's what we hope to do. If we can do that to this accuracy, then yes, the CCD effects are the dominant remaining systematic.
This is probably a silly question, but do you have to worry about time-dependent effects in the CCDs?
Oh boy, that's a really good, that's not silly at all. I mean, so what things can change with time? Voltages can drift and change, but then of course we can measure them. The polysilicon electrodes, I think, are not going to move. The doping isn't going to propagate unless we warm it up a lot, unless we cook the CCD. If you accidentally deposit some garbage on the surface, it's not going to change this effect. It's going to affect the photometry, but not this effect. So I think it's safe to say that if our voltages are under control, no.
What about charge transfer efficiency?
Well, charge transfer efficiency is something that will change with time and space because of radiation damage. But happily, we're not in space. I was once asked, by the way, by Charlie Pellerin at NASA if they could launch LSST. I'm glad I said no.
Shall we let Steve Kahn ask a question?
Yeah.
Well,
Yeah,
I just wanted
What the hell? Right.
I wanted to comment on Martin's question and actually give credit to our chair for devising a very clever scheme for actually monitoring some of these effects in the dome. So we'll characterize them in the lab, but we'll have this spot projector actually in the dome that will allow us to check this as a function of time. So I think it's probably not going to be an issue.
Yeah, good question. Okay.
Good answer.
All right, shall we thank Tony one more time?